Hello. We are going to go over 4.2 Theoretical Probability, Friday, January 15th. So our goals are to define probability. We're going to identify the differences between experimental probability and theoretical probability. We're going to define simple event and complementary event. Hopefully some of these phrases are familiar from 4.1. Note number 1. Probability is the likelihood of an event occurring. Experimental probability uses data collected in a simulation or experiment to determine the likelihood of an event or if that event will occur. Experimental probability is limited since the data size is often small. Basically, it means that there are a few trials are done. Okay, so a few trials are done. The formula, though, for theoretical probability is similar, well, it's the same, to experimental probability. Written more formally, though, is the probability of A, event A being the desired outcome, is equal to the number of desired outcomes divided by the number of outcomes in our sample space. That's a more formal definition versus the one that we had earlier, which was the probability of A is equal to number of times or number of desired outcomes. That'll work too. Divided by the number of total outcomes. Okay. So P bracket A bracket is the probability of event A. That's our desired outcome. N bracket A bracket is the number of times that outcome A occurs. It's also called the event space. Okay, so event A being what we want. And N bracket S bracket is the number of all possible outcomes, also called the sample space. Okay, so when the value of A, so the number of desired outcomes is equal to 1, then the probability is called a simple event. Okay, and given enough trials, that's the key, right? The experimental probability is equal to the theoretical probability. So we had this was the theoretical probability formula, all right, versus this one is the experimental. All right, so they're similar because they are. One is more formal, one is more relaxed, but they do actually find the same thing. Okay, so in class, on our Google Meet session, we filled this in. So we said, have everyone in class roll a die, record the frequency of each roll in the chart, and use the chart to answer the following questions. So this chart, this is all experimental, so it's going to influence the values for experimental probability. Okay, so we had the values of 4, 2, 2, 2, 1, 1. I said we needed to add them up. So 4 plus 2, 6 plus 2, 8 plus 2, 10 plus 1 plus 1 would be 12. So that is equal to the total number of people, which is equal to the total trials. It's also equal to the total outcomes. Okay, so if we want an experimental probability of rolling a 5, okay, so that's A, we have to look at the 1. So the probability P bracket 5 bracket is equal to 1 over, and the number of trials was, I think we got 12, right? So 1, 5, and 12 trials, or 12 participant, 1 participant per trial, okay? Now the theoretical probability would occur, we're still trying to find the probability of a 5, okay? It would be influencing, or it would be influenced by our sample set and our event set. So what does that mean? Well, it means that the observable outcomes that we would be happy with was 5, okay? So 5 is the value, but how many of those values are in that bracket? There's 1, okay? And then all the possible outcomes would be the number of sides on a die. So theoretical, it does not require me to pick up a die, okay? So I am not picking up a die at all, okay? So here, the total number of outcomes would be 6, because I could get a 1, a 2, a 3, a 4, a 5, or a 6, okay? So there are 6. So it's the number that we're getting. How many of them are in each of these sets? All right, the probability of rolling a 3, so the P bracket 3, and I said during class to make sure you use your correct notation. So for 3, that would be here, and there were 2 people that got a 3. So it would be 2 people got a 3 out of the 12 people in total. Reduce whenever possible, so that's 1 out of 6. Now that's really good, because when we check the theoretical probability, we have the number of desired outcomes. So when will we be happy? Only when we get a 3. Okay, so there's 1 time that we are happy, specifically when we get this. And then in the brackets for the sample space, we can get a 1, a 2, a 3, a 4, a 5, and a 6. So the set notation contains what the outcome is, and the number of those outcomes is what becomes the probability, okay? Okay, so it's the number, okay? And then these are all the outcomes, okay? So you list outcomes, all right? Rolling a 4 or more, so that would be a 4, a 5, or a 6. So that would be these in C. So you'd add 2 plus 1 plus 1 is 4. So the probability of rolling a 4 or more, that's a greater than, right? So the probability is going to be a value of 4 or more. So you could write greater than or equal to 4. Okay, so 4 or more. So the 4 means you're also equal to, all right? So the probability of getting something greater than or equal to 4 is equal to 2 plus 1 plus 1. So in total, 4 people got a 4 or more. So they got a 4, a 5, or a 6. And then divided by the total number of participants, which were 12. So you divide it here by 4. So 1 out of 3. So the probability theoretically would be the probability that was greater than 4. Okay, so your desired outcome was equal to or greater than 4. So that equals to how many outcomes am I going to be happy with? Well, I'm going to be happy with a 4, a 5, or a 6. So there are 3 items that I'm happy with, so that's the numerator. And then the possible outcomes are 1, 2, 3, 4, 5, 6. So the sample space represents the list of outcomes, and then the probability tells me how many I have. So 3 out of 6, so that gives me 1 out of 2. Okay. 0.33 repeated 0.5, they're not the same. They're not expected to be the same. Only when your theoretical probability is based on a large, significantly large number of trials, maybe 100, will they get close to being the same. Okay, so rolling less than a 4, so that means you're rolling a 3, a 2, and a 1, right? So that's your desired event space, right? So you look up here, so a 3, a 2, and a 4, all of these people here did just that. So that's D. So 4 plus 2 plus 2 is 8. So the probability of something less than 4 is equal to 8 out of 12. And then you could divide that by 4. 2/3. Okay, so if you want the theoretical probability of rolling less than 4, okay, depends on how many outcomes are favorable. Okay, so we said over here, well, the outcomes that are favorable have to be less than 4. So they're 3, 2, 1, or 1, 2, 3. Okay, so that's my event space. The number of those objects is the numerator in the probability, and the number itself, I'm going to have to move over here because I'm going to need to reduce, so I'm just going to move everything over. 1, 2, 3. Okay, so the number of desired outcomes, I'm okay with 1, 2, 3. In fact, that's what I'm hoping for. Out of the total number of outcomes, well, that's 1, 2, 3. So notice 4, 5, 6. Notice the sample space is not changing, right? Which should make sense. So that's the number, right? The number of objects. Okay, so probability is the number of objects. And then you could reduce that to 1/2. All right, so rolling a number greater than 2, so something greater than 2 is equal to 3, 4, 5, 6. So that's my event space, right? Event space, right? This is the event space. Right, based on the description. So how many are there in the experiment, right? So 3, 4, 5, 6. So that would be E. So 2 plus 2, 4, 5, and 6. Okay, so in total there are 6 people. So greater than 2 probability, bracket, greater than 2. So there were 6 people out of 12. Okay, and then for theoretical, it's based on facts. Okay, it's based on experiments. All right, or simulation. All right, so we go probability. So it's rolling a number greater than 2. So greater than 2 is equal to, so our event space would include numbers such as 3, 4, 5, 6. Okay, so how many of those objects are in the event space is the same as the number in the numerator, 1, 2, 3, 4. And then for my sample space, it doesn't change because I'm still rolling a die, so numbers 1 through 6. How many are in the sample space is the number I'm writing here in the probability question. Okay, and then I reduce that. Okay, not always are they equal. We found that they were equal here, but it's very unlikely that they will be. Okay, I'm going to check my time, see how I'm doing here. All right. Complementary event includes all events that are not in the event space. A with a hash mark there means the complement of A. Okay? So it means i.e., in other words, everything that isn't A. So if I talk about this would be the sample space, and this would be the event space. Okay? The complement, it's the complement. Okay? It's the shaded. So everything that's not A. The formula for the probability of the complementary event, is A, the probability of the complementary event A is equal to 1 minus the probability of A, right? So hopefully it makes sense. So 1 is the whole space, okay? So the sample space is equal to 1, okay, as a probability. And then this is always going to be a decimal, right? So 1 minus this decimal amount has to give you the shaded area called the complement, okay? We're going to do example 2 in video part 2.